So hello everyone, this is lecture 9 for the quantum mechanics. In the last lecture we did up to here, Davison-German experiment, and we discussed already the de Broglie hypothesis. And in the proof of this experiment in the Davison-German, they proved that every particle or matter should have your wave nature, and they proved it for the electron. Okay. Now try to solve these questions based on the de Broglie hypothesis. So this is something like this, means try to solve them, otherwise I will provide the solution definitely in the next lecture. So find the de Broglie wavelength of electron whose speed is 10 to the 8 meter per second. Same electron whose speed is 2 into 10 to the 8 meter per second. Then second question, find the de Broglie wavelength of a 10 milligram grain. Okay, this is the weight of sand blown by wind at speed 20 meter per second. Find the de Broglie wavelength of the 40 kilo electron volt electron used in a certain electron microscope. So this amount of energy electron used in the certain electron microscope, so you need to find the de Broglie wavelength for this. Okay, so energy is given. Find the de Broglie wavelength of a 1 mega electron proton. So find this for a proton and a particle have the same wavelength. Sorry, this is photon. So photon and a particle have the same wavelength. Find the linear momentum of photon and particle. Compare the photon energy with particle's total energy. Compare the photon energy with particle's kinetic energy. An electron and a photon both have kinetic energy equal to 50 kilo electron volt. Are their de Broglie wavelengths equal? If not, and if yes, what are the values of the wavelengths for each? Okay, so try to solve these questions. In the next lecture I will give you the solution. So today's our topic is, means we have seen that in the Davison-Germer proved that the electron have the wave nature, and de Broglie gives this thing that every matter should have wave nature. Then okay, let's because this is proved, then that this is true. So what is this matter wave and how this looks like? So that is a big question, means still we have not the any answer of this. Means let me tell you what we don't have. So matter have and matter wave and wave packet. Okay, so what is matter? Matter have particle nature and matter have wave nature. And this is something like when it have particle nature it won't have wave nature, and when it will have wave nature it won't have particle nature. Okay, so one will collapse when there is another. Okay, it's something like water, it can be ice or water. Okay, so when you are dealing with ice there is no water, and when you are dealing with water, then there is no ice. Okay, so this is something like that. Now for matter wave we know what is the wavelength. If it is particle, the lambda will be h upon p. That's how this relates from the de Broglie hypothesis. Now the biggest question which is not answered till date, if electron is a wave, then what is the physical quantity that is varying in such wave? So what is the thing, means in the real waves we know that there is always something oscillating, then what is oscillating in the electron wave? So that is the biggest question which is not answered. Means let me give you an example. If we have EM wave, then we know it is made up of electric field and the magnetic field. So E field is given by E0 cos omega t minus kx. So in it the electric field is oscillating. Same for this magnetic field, B0 is oscillating, and we know this amplitude of electric field is changing, that is in volt per meter, and for B it is Tesla. So that is changing and oscillating. So we know that are measurable quantity. If we talk about sound waves, then in sound waves we know pressure is changing, and because all the sound waves travels in the means because of pressure change, rarefaction and compression, that is, and when there is compression pressure will increase, when there is rarefaction then pressure will decrease, and that's how our sound travels. So we can write this sound wave in terms of pressure, and this is your, means this is also a wave. So same if we talk about the water, then inside water we have elliptical waves. So in that only the particles of water surface is oscillating, and if we talk about a rope, then whole rope particles are oscillating. So that's how we can see that there is always something measurable quantity which is oscillating in the waves, and these are the real waves. Now if we talk about the matter wave, they are saying that the electron have the wave nature or any particle have the wave nature. Then what is oscillating in that wave? Okay, means when there is wave nature there is no particle nature. Then in that wave what is oscillating? Because there is no particle, then it can't be particle itself, because when there is wave nature there is no particle nature. So what is oscillating in that? So there is no answer for that. And but means they don't have any that qualitative idea, but what we need here is quantitative idea. So we use the mathematics. Okay, means we don't know what is it look like or what is this matter wave, but we can take the harness this thing by using the mathematical things. So let's say if this is a particle and it is having wave, then definitely we are seeing that in every kind of wave we have this thing constant, means this is something oscillating in that, and this can be written in this form. So let's say we assume that that wave which is forming, which we don't know, that should also be look like something this, means this should have the same equation, and there is something which is oscillating we don't know, so we put it a and we write it this as phi psi. So we don't know and we call this as wave function. Okay, this is just a intuition based, means there is no logic behind this. So this simple logic is that that wave is oscillating and that should have this kind of cosine or sine function. Okay, so this was the intuition or the idea. Then there was one more thing. At that time Max Born gave this interpretation for this matter wave, means let's say we have electric field, that is E naught cos omega t minus kx. Now see, in the radiation, when the square of this electric field gives you the intensity, and intensity is nothing but number of photons falling per unit area per time. So when you know the intensity, you can know that how much photons are falling and at what area, so you can tell all the information about that. So same we can talk if we are talking the analogy, then here square of amplitude is giving you about information about the particle or how much particle is there. Okay, so same they compare this, and analogy gives us that square of this, if there is this phi naught and the phi, then amplitude of this square, this wave, means amplitude of this amplitude of the square of this wave. Okay, square of the amplitude of the wave. So that must give you something information about the particle. Okay, means when it is in the wave nature, then the square of the amplitude of that wave must give you information about that particle. So he said that, Max Born said that this amplitude square is nothing but probability of finding particles at time t at a particular position x. So that was our thing which we started, because we don't know the particle nature, means the physical thing we don't know, but we can't stop at that point. Okay, so we'll see that if we in the future we will see that what is oscillating and all. So but we should move forward. So that's how we move forward, and we Max Born assumed that this is nothing but probability of finding particles at time at a particular position x. So and we call this probability density. Now if we need to find probability density between x and some point dx, then we call, means we can write this as this form. This is nothing but probability of finding the particle at time t in the region x and x plus dx, where dx is very small. Now if you need to find a probability density between a point x1 and x2, then that can be written in this form: x1 to x2 phi xt square dx. This is nothing but probability density of finding the particle at time t in the region x1 and x2, and it can be a very large interval also. And when we see that this is representing probability, the square, then we can call this wave as probability wave. So that's just, there is no meaning, no logic, just we call this probability wave. So if according to this we can write, means because of these analogy, we can write this wave in this form. So let's say if this wave is in this form, then this should be look like this. Okay, and if there is some particle here, then definitely if there is probability wave, okay, then probability wave will be having higher amplitude in the nearby this region and less amplitude in the other regions, because this is probability and this is probability of finding the particle. But see, the square of this wave, amplitude square, will give you the same, means it is giving same probability at all points. Okay, so now this can't be possible, because particle probability can't be same at every point. This is not true. So that's why we find it that there is something wrong with this equation for the matter wave. There is something wrong with this equation, because this can't be true. If particle is there, this probability can't be same everywhere. So phi square probability is constant from minus infinity to infinity according to this equation, and phi xt a cos omega t minus kx can't be the expression of wave function of free particle. So that's why this can't be the expression, the real expression for the probability wave or the matter wave. This can't be the expression. So that's how we proved this. Now what kind of expression this should be? So see, that we'll see in the next lectures. But now the graph should be look like this. Means if this is your wave function, this is representing probability, then if there is, you have your particle here and it turn out to be wave, means now in the wave nature, the probability should be more somewhere this region, in this region, and less in the other regions, because we are just interpreting this thing, means the wave nature of particle. So when there is wave nature, there is no particle, then the wave should represent the particle's density, means that should represent the probability of finding the particle somewhere. Okay, so here it was, if the particle was here, then this wave should look like this, means the amplitude should be large here and less in the here, and when we go to the infinity, that should be 0. Okay, and we call this thing as wave packet. Okay, and wave packet, and from the mathematics we know this how the wave packet form. Wave packet form from the superposition of large number of waves, each having the different wavelength. So there are different wavelength waves, so when they all superimpose, they gives the wave packet. We know this. So this was assumed that there are large number of monochromatic waves, and this is something like this. So different frequencies we have, different wavelengths we have, and when they superimpose, they will give you this wave packet, and that's how they define this matter wave. Okay, means for a particular particle, the wave should look like this, a wave packet. So that was the interpretation. So that's it for the today's lecture. In the next lecture, we will see some mathematics of this wave, means how can we, if it can't be described in this way, then how can we describe it in mathematically. Okay, so we'll see more about it. So that's how we are starting to the true quantum mechanics. So we'll see you, I will see you in the next lecture. Thank you everyone.